Hello, Ming-Feng from UC Riverside. So today I will talk about how to use multi-fidelity emulation to cheaply emulate your summary statistics. I will cover one published paper and two ongoing projects, including emulating Lyα Flux power. The outline of this talk, I will first talk about what's the problem, why do we need multi-fidelity, and I will talk about what's emulation, what's multi-fidelity, and then I will give three examples, including meta power, emulating different box sizes, and emulating Lyα Flux power. So the problem here is that the current bottleneck of emulation is on the cost of simulations. You can imagine as the future surveys getting more small-scale structures, the simulations have to be more realistic and more expensive to match the resolution requirements. That means the training simulations length itself for the emulator could be very hard to generate. For example, Euclid Emulator 2, they used more than 200 simulations in 3000 cube particles in 8 dimensions. This is not a computational budget every group can run. In the future, we also want to emulate beyond lambda CDM cosmology, which means more dimensions. This bottlenecks largely limits the future model developments and also limits the model space we can explore. Therefore, a new emulation framework needs to be proposed. And one of the solutions is multi-fidelity. But before we jump into multi-fidelity, let's talk about emulation. The history of emulation is that the linear model calculation is no longer enough for the observations we have on a small scale. This is a problem because simulations are expensive. The proposed solution to this problem is to replace the simulation using a surrogate model. Usually a surrogate model is doing the interpolation, and so you need a experimental design in the parameter space running simulation suite in a space-filling hypercube. And then you can use this surrogate model to do whatever outer rule applications you want, like the uncertainty quantification, inference, and optimization. Another view of emulation is the Bayesian aspect of emulation, which you treat the surrogate model as a prior over functions, usually as smooth functions, and you treat the experimental design as the data. And the Bayes rules tells you if you have the prior, you have the data, you will have the posterior, which are the simulations you haven't run. And as you may know, the natural choice of a prior over smooth functions is a Gaussian process. Gaussian process as a prior guarantees you have a smooth and monotonic features of the response surface y-axis. The interesting idea or the interesting Bayesian attitude here is that you are not really trusting your prior giving you the correct function form. You are assuming a very, very flexible prior, allowing you to have as many function shapes as possible. And just allow the Bayesian machinery to condition on the data, give you posterior beliefs on the function form. That's why choosing different machine learning models actually does not really matter a lot in this case, because you are always having a flexible prior allowing many function shapes as possible for the emulation problem. So how many different emulators on the market right now? I don't know. It's hard to count since there are so many combinations. But in principle, I summarize here, you have three ways to change your emulation. You can change the training simulations, you can change the surrogate models, you can change the summary statistics applications. For example, the first Cosmic emulator from Hetman should use n-body simulations, surrogate model using Gaussian process, emulating on meta power. For the recent CMOS projects, they use hydro simulations in small box, surrogate models using neural net, emulating on field level. In this talk, I will talk about the first two examples are n-body simulations applying on multi-fidelity Gaussian process, emulating on meta power. The third part of the talk I will talk about using hydro simulations, multi-fidelity, and emulating on the Lyα Flux power. So idea of multi-fidelity is simple. You use as many low-fidelity simulations as possible to explore the parameter space. Use a few high fidelity to just calibrate the resolution difference. An analogy here is that in academia, professors are high fidelity, students are low fidelity, but the university won't be able to hire tons of professors to do research. The solution here is to hire as many students as possible. Students do the hard work, exploring different topics, and we only need a few professors to calibrate students' results. In this way, we can get both efficiency and accuracy. So the popular multi-fidelity method is the Kennedy-O'Hagan method, or KO method, developed in 2000. So KO method models a sequence of simulations from lowest to highest using a linear autoregressive framework. On the left-hand side, you have high-fidelity emulator. Right-hand side, you have the low-fidelity emulator times trainable scale parameter plus a bias function model as a Gaussian process. And it is proof that you can train the KO method recursively, which means you train the low-fidelity emulator first, and sampling the posterior from low-fidelity, use it as the input for high-fidelity, train the rho and delta as another GP. So effectively, you're training two GPs here. The nonlinear GP is an improved KO method using the DGP, where you assume the scale parameter is a Gaussian process, and which has the input for both cosmologies and the output from previous fidelity. In this way, you can have a scale parameter which modeling the correlation between low and high fidelity to be a function of cosmology. So in our first example here, we have n-body simulation trying to sample in 5 dimensions, Hubble, total density, baryon density, and amplitude of primordial power spectrum and spectral index. You have low fidelity design in Latin hypercube in the blue dots in the figure. You have high fidelity, which is a subset of low fidelity Latin hypercubes. Orange dots here, which are optimized using the low fidelity simulations as a prior. What we are trying to do here is the resolution difference times 60 times greater in the particle numbers for the emulation. So the result here I show is that I show the emulation arrows in the y-axis. X-axis is the K-scales for power spectrum. You have orange the single fidelity emulator using 3 high fidelity, green one using 11, and the blue one is the multi-fidelity using 50 low fidelity, 3 high fidelity. As you can see, multi-fidelity achieve 1% error on average. So, and the quality of low fidelity simulations matters. It means that you can downgrade the low fidelity, and then you get worse multi-fidelity emulation. If you upgrade the low fidelity to higher resolution, you get better multi-fidelity emulation. So in this case, we have orange arrows by using downgraded low fidelity simulations, which you can see the emulation on the small scales getting worse. And if you upgrade the low fidelity number of particles to be higher, you get much better emulation. So one question arises is that, can we use small box, low fidelity to improve the small scales emulation? With no number of particles in a simulation is a fidelity variable, but the box size is also a fidelity variable. Smaller box size, better resolutions at small scales. So the idea is to combine large box and small box in low fidelity through a directed graph design here on the left hand side. So the directed graph here, I show large box in L1, small box in L2, and we want L1, L2 resolve the same high fidelity simulation. Graphical model GP proposed by JIT 2021 allowed us to do so. This is a modification from NERGP model where you just expand the input space for the row function to include the output from the second low fidelity node. And here, the special thing is that we include a linear kernel for the output from previous fidelity. This makes sense because linear kernel in Gaussian process is basically doing Bayesian linear regression. And what we are trying to do here is do the linear regression from the L1, L2 to predict the high fidelity. So here we show the arrow plot for the different multi-fidelity model, AR1, the KO method, and the graphical model, Gaussian process in yellow line. And you can see the graphical model GP outperforms other two models on the small scales because it has the help from small box. And on left hand side we show the redshift average error for redshift from 0 to 3. Right hand side we show the average error as a function of redshifts. On all of these redshifts, the graphical GP1 outperforms other two models, but especially for redshift larger than 1. To sum out, we just want to show that it is possible to emulate the high fidelity using the low fidelity from various box sizes. The final example would be the Lyα Flux power. And here we showed that we have two different resolution simulations, and we run the hydro simulations using MP Gadget. For each snapshot, we draw sidelines, many sidelines, random sidelines in the snapshot, generate the Lyα forest, and for each sideline, we measure the correlation between the hydrogen absorptions to the Fourier transform, get a 1D flux power spectrum. Our experimental design is in 9 dimensions. So we not only have the lambda CDM parameters, we also have the reionization parameters, including the helium-2 reionization ratios and the peak temperature for helium-2, and the ratio for the hydrogen reionization and the black hole feedback parameters, controlling the amplitude of black hole feedback. And as you can see on the right hand side, we have high fidelity power, low fidelity power, the ratio between low and high fidelity in different ratios. The discrepancy between low and high fidelity appears across the K scales and also appears across the redshift space. So this is a much harder problem to do. However, as you can see, in this arrow plot, we summing over the redshifts, you can see the multi-fidelity emulations is much better than just using single fidelity. On the right hand side, you have the prediction errors versus runtime. You can see the multi-fidelity emulation actually scales pretty well. You get very good accuracy using very low runtime. But the key point of this work is that it is possible to apply multi-fidelity emulation on the hydro simulations. In conclusion, you can save the budget using multi-fidelity emulation. You can directly apply this method on your simulation suite. It can cheaply increase your dynamic range of simulations. We provide 3 examples. First one, meta power. Second one is possible to apply different box sizes. Third one is possible to apply it on the hydro simulations, emulating the Lyα Flux power. We plan to do it on the Helmholtz function and cosmic shift power in the future. Finally, if we want to thanks EG and Simon Mark for kindly providing their graphical GP code in Python. Thank you all.